So we're going to start this lecture talking about Lewis dot structure, its theory, valence electrons, core electrons, etc. Now up to this point, when we've done electron configuration, what we have seen is that we have to take into account all of the electrons that are surrounding the nucleus of an element, where they're located and the order in which they fill. From here on out, we're going to completely ignore the core electrons. We're only going to deal with the valence electrons. It's not that we don't care about core electrons, they're very, very important, but the valence electrons are the electrons responsible for bonding. So these electrons are why things bond. Okay, so this is going to be our Lewis dot structure. All we're doing is we're using dots to represent one electron surrounding the element, and we're going to use the element's symbol. So you can see oxygen here. If you look at your periodic table, grab your periodic table. If you don't have it, pause and go grab it. You will see that oxygen is in group 16 on the periodic table. Group 16, they have 6 valence electrons. Just a reminder, group 17, they have 7 valence electrons. Group 15, 5 valence electrons. 13, 3. We're going to only deal with the valence electrons for the representative elements. Remember, for transitions, I would have to tell you how many electrons are gained and lost, or I'm sorry, are lost, because they're not consistent, they're not regular. So you'll know that by the charge. The charge that it becomes is indicative of how many electrons it loses. So if I tell you Fe2 plus, you know that iron has lost 2 electrons. Okay, so for the transitional, for this purpose, for Lewis dot structure, I'm ignoring them. But when we get into naming and forming ionic compounds and reactions, we'll go more into the transitional metals. So if I were to draw the Lewis dot structure for carbon, I'm going to say, okay, I'm going to start with writing my letter C, and I'm going to look at my periodic table, and here it is, and I'm going to say, okay, carbon is in group 14, okay? It's going to have 4 valence electrons. So I always start at like 12 o'clock and go clockwise and then double up. So for carbon, it'd be 1, 2, 3, 4. Because of the octet rule, meaning elements want 8, there are exceptions to that. Like, for example, boron is an exception. It doesn't need an octet, doesn't want an octet, so it won't do the special things that normally elements would do, like double bond or triple bond, in order to make an octet. But because of the octet rule, meaning, again, elements want to have that octet, those 8 valence electrons, either in and of their own right, like noble gases, which already have 8, or by way of bonding with something else. So they're sharing, but both entities feel like they have 8. We can see that carbon can bond 4 times because it's missing 4 valence electrons. Ergo, we can get things like CH4. Now, you'll see I wrote lines. Lines represent a shared pair of electrons. So if I go back to carbon's Lewis structure, and I look at hydrogen's Lewis structure, what we're going to see happen is these are going to be the ones that are shared. Carbon is now sharing a pair of electrons with hydrogen, and hydrogen is sharing a pair with carbon. So this Lewis model, we basically just use it to show how compounds can be formed by way of gain and loss or sharing of electrons. So if we go back and remember electron configuration, if we have regular old ordinary potassium, Here's the electron configuration for it. When it becomes an ion and it becomes K plus 1, it loses one valence electron. And so now this becomes its electron configuration, and in its next highest orbital pathway, there's a total of 8 valence electrons. Okay? So again, the octet rule guidelines is just that non-metal period 2 elements must obey the octet rule. Non-metal period 2 elements. So that is period 2 is this row here. That's 2 right there. So the non-metals are over here on this side. Okay, so this is our period 2. So the non-metals that we're talking about are carbon, nitrogen, oxygen, fluorine. Okay, they will always do that. However, boron is the one exception. And it's an exception because it's not full and of its own right a non-metal. It's a metalloid or a semi-metal. We can have expanded octets, which means more than 8. We see that with like the bigger, heavier metals when they're bonded with a non-metal. Exceptions to the octet rule, meaning they don't need an octet. Hydrogen, and that should make sense because the only thing it has is a 1s sublevel, main and sublevel, where the most it can hold is 2. It's like saying I want to put 6 people in a 2-seater car. That doesn't happen, right? So it can never have an octet. Lithium is an exception for the same reason. Beryllium and boron. Boron could form an octet, but it won't. It doesn't want it. It's not stable that way. It's just fine having 6 electrons. Oh, and helium. All right, so when we use the Lewis model to predict a formula, if I do calcium and chloride, I'm going to see that calcium has 2 valence electrons and chloride ion has 1. So in order to, for these two to come together, chlorine now has an octet. I can rewrite this like this. But calcium still has an extra electron. And so that means another second chlorine can come in and take that from the calcium. So now I have a second chlorine that's going to share. And now these in here are going to form a bond. So we can predict this formula to be CaCl2. Okay? Now, metals in a formula, the metals are always written first in an ionic compound. The non-metal is always written second. If it's a molecular compound, meaning all non-metals, then the one with the most metallic character is written first, or the one that's furthest to the left and down on the periodic table is written first. Okay, so Lewis theory predicts the number of electrons a metal atom should lose or a non-metal should gain, but just simply by looking at the valence electrons. Calcium has 2 valence electrons, therefore it will lose 2 and become a +2 to have that next lower level being 8 valence electrons, and the octet rules is good. Also, the octet rule guidelines allow us to predict this as well. So a couple of takeaways from Lewis theory that I want you to be aware of. This one this one. And I think the other one is on the next page. But it predicts that moving ions out of position, therefore, will be very difficult. So because moving ions out of positions, meaning metals with nonmetals, it's very, very stable. And so moving those ions, it's not going to be very easy. It's going to take an incredible amount of energy. And so therefore, ionic solids are hard. Okay. If the ions are displaced from their position in the crystal lattice structure, repulsive forces should occur because you're going to get full in and of their own right charges that will repulse them each other. So let's look at the crystal lattice structure. So the crystal lattice structure is literally a structure formed by ionic compounds, and it's just like what it sounds like. It just means that every cation will be surrounded by anions because of those attractive forces with the positive and negative charges. So takeaway, crystal lattice structure maximizes the attraction between cations and anions because it puts them into a position to be attracted to each other. So this is a good example of a crystal lattice structure. Literally think of like the lattices that the climbing plants grow on, like you can buy at Lowe's or Home Depot. That's kind of the structure they form. So lattice energy can be measured directly, but it's calculated from other processes. So let's just go back one slide. When we talk about ionization energy, being of the metal being endothermic, meaning you got to put energy in or heat in to pull off that electron. An electron affinity of the nonmetal is exothermic, meaning when it takes that electron, it's going to release heat. When these two things are happening simultaneously, we get ionization energy of the metal that's larger than the electron affinity of the nonmetal. So it's harder, it takes more energy to remove that one electron than it does with the energy released from the chloride ion gaining that electron. So when we talk about heat of formation, we're talking about the heat and energy involved with forming bonds and breaking bonds, okay? When the heat of formation of the ionic compounds is exothermic, then in large, it's because of what's going on with the removal and gaining of an electron. So we know something just by looking at the delta H's, if it's exo or endothermic, because, excuse me, a positive delta H is what tells us it's endothermic, meaning you have to add heat or energy in. Exothermic is always negative, indicating the negative, it's going away. Heat is being released. So lattice energy, how high the lattice energy is dependent upon the charge of the metal and the distance or size between the nuclei of what it's bonded to. So if I were to look here and say I have just some solid sodium chloride, you know, just regular table salt, and I have these probes in here and I'm trying to light a light bulb, that's not going to happen. The light bulb is not going to light, and it's not going to light because there's no electron flow. When there's electron flow, there must be ions in solution because that means electrons are moving, right? So when I have ions in solution, they're ions in solution because electrons are moving. Electron movement is what allows the electricity and the light bulb to light up. So solid sodium chloride, they're neutral. They're good. They're bonded. They're solid. As soon as I add water and they break apart, electrons are moving. Once I have this solution here with charges, the positives are going to go to the one side, the negatives to the other side, and some of them will be attracted to each other and the water. And that movement of electrons is what allows the light bulb to light. So just to summarize the ionic compound formulas, they're always going to be positive and negative ions. Excuse me. In a chemical formula, the sum of the charges must net to 0, or the overall charge in the compound. So when we have any of these written just like this, we know that overall they are neutral because there's no outside charge written. But when I have this, for example, we know that overall this whole thing has a 3 minus charge. What's another one? Overall, this whole thing has a 2 minus charge. So the charges of everything need to add up to whatever the overall charge is on the compound. And the formula of an ionic compound represents the smallest whole number ratio of ions. So again, calcium and oxygen. Calcium will be 2 plus. I'm just going to review this. All of group 1 will be plus 1. All of group 2 metals will be plus 2. Group 13 metals will be plus 3. Group 14 metals, for the most part, are plus 4, but these two down here can be plus 4 and plus 2, and that's lead and tin. Okay. All of group 17 will be minus 1 because they have 7 valence electrons, so they'll gain 1 electron. All of group 16 will be minus 2 because they have 2 valence electrons and want 8, so they'll gain 2 electrons. And all of group 15 nonmetals will be minus 3 because they have 5 valence electrons and want 8. So the quick and dirty way of doing this, and what compound will I form, is to do the switcheroo. Just bring the subscript down and then reduce it as far as possible. Okay, I can both reduce these and divide each one by 2. So the formula is just CaO, and the charge on calcium is 2 plus. The charge on oxygen is 2 minus. That nets out to 0, so I'm good to go. Okay? If it were magnesium and a fluoride ion, and I did my switcheroo, it's just going to be MgF2. Okay? Yeah, let's do aluminum and nitrogen. So aluminum is in group 13, so it'll be a 3 plus charge. Nitrogen is in group 15, so a 3 minus. If I just bring these down, then I get Al3N3, but I can reduce it. So just ALN. So now let's do this with aluminum and oxygen ion. I'm still going to do my switcheroo. So I'm just going to have Al2O3. And that's it. We're going to stop with Lewis structure there. The next segment will be on naming ionic compounds. I suggest having a just sheet of paper and use it in landscape, and we're going to write a bunch of different stuff. Okay? All right. I will see you guys soon.